Thornton. He has a degree in computer science at Mississippi State, like I do, so we already know that he's very cool.
Obviously.
He'll be discussing SCADA, a virtual SCADA laboratory for cybersecurity, pedagogy, and research. So, please welcome Zach.
Hey guys. So I'm trying to get this started, so you may need to give me just a minute. So I may run through the slides quickly once I get it set up. So I thought it was going to be a little quicker getting it set up. So give me just a few minutes. I think y'all will be glad you did. You can talk, don't be afraid.
So is SCADA like a Mississippi State pastime or something?
No, no, why do you say?
Well, I'm at UAH with Dr. Vaughn, and then Dr. Vaughn, that's what he talks about whenever they ask him. I mean, Russ will talk to me about it. So, 3 for 3 at this point.
Well, it just happens that, like, Dr. Vaughn, I think, got Dr. Morris working in it, and then I worked for Dr. Morris, who worked for Dr. Vaughn, so it probably all traces back. And then I worked in paper as a controls engineer, so we were, like, programming SCADA stuff.
It's
So,
also the hospital's a pretty good landing spot for your graduate engineering.
This is true.
It's real funny, too, because Dr. Vaughn is trying to get Professor Dr. Morris to come over to UAH. So, are you guys at UAH? Okay, nice. Yeah, you may see Tommy over there before long.
Looking forward to it. Security. I don't know anything about security. For sure.
Wow. That's it. So you guys are students. You also students?
Yeah, good to Calhoun.
Okay. And where are y'all from?
I'm taking classes in Calhoun in their IA program.
Okay.
ICS and SCADA distributed generation.
Oh, okay. I think you may be interested in what we're working on. Let me bring it up and we'll start. I'm almost there, I promise. There we go. There we go.
Yeah, during the last one, I thought you were sitting in the back, like, waiting for a question. I was like, ignoring the crap out of you. And then I finally realized you have times written on there. I felt better.
Okay.
Poor guy.
Cool. So y'all ready? Sorry, it took me a little while longer. But yeah, I'm Zach. I actually work right now as a research associate for the Distributed Analytics and Security Institute, which is Dr. Morris and Dave Damp here at Mississippi State. I'm working on my master's too. So what I'm showing you is our research, but it's also what we're working on at DASI in part. So obviously couldn't get by without this. So sorry guys. Moving on. So you guys already heard a little bit about what SCADA systems are, right? I don't really have to. Yeah, so you know they use as control systems in a lot of these industries, right? Yeah, cool. This is real familiar to me. I worked for 2 years as a process control engineer in a paper mill. They do stink. So anybody smell a paper mill? Yeah. Yeah, they're terrible. I came home, my sister was like, "This smells like dead rats in your car." Yeah, it's terrible. But, so yeah, they use controls in here. And one of the things that y'all just heard Ben talk about, I think is real interesting. He said that you have to know normal before you can know suspicious. One of the things about all these industries is none of them want to give us gobs of network data. Like, nobody wants to just say, oh, here's my data for all the communications for all the controllers in my power generation facility or my nuclear plant. I mean, nobody gives you that. So that's going to tie into what we're doing. But yeah, SCADA controls stuff like this. I apologize for hitting too many buttons. But did they kind of break this down too into like a hierarchy of components for SCADA systems when somebody talked about it? Maybe? Okay, that's fine. I want to do it for you. Most of the time when we break down a SCADA system into 4 components. At the root level, we talk about sensors and actuators. That's the basic stuff. Like, you have to have a pressure sensor to know what the pressure is in some system. You got to have a valve to open up so that you can release pressure in the system. That's usually my go-to example for a sensor and an actuator. Actuators could be anything. It could be when you like close a relay and then you've now got voltage on whatever that line is. That's an actuator. Those are what actually do the controls. They're controlling the physical world. So sensors and actuators. Controllers are usually the targets for cyber attacks, where the sensors, they feed the data into the controller. And so it's sometimes it's just like a 16-bit microprocessor, but it's encapsulated. It has an analog to digital converter, digital to analog. So that's what's doing the controls. Sensor reports data. Control says, like, okay, pressure is at this point. Now I need to affect something. So controllers make the decision on how to open or close a valve, how much to open or close it, turn on and off a pump, that kind of thing. HMI it's the same thing basically as a GUI in modern times. It's a display, so you can see the whole process going on. So when an operator is sitting in a control room, he's looking at a display. So HMI. Supervisory control will usually sit, so if you have sensors reporting to controllers reporting where you can see it on an HMI, the controllers will go up to supervisory control. That's kind of confusing, so here you go. So see, in this case, you would have maybe a sensor, he's reporting, if you're talking about robotics, it's usually reporting position. So like, think a car manufacturing facility, they're stamping some steel. So this says, okay, the stamp is closed. Reports it up here to the controller, which is, these are just microcontrollers that are encapsulated in boxes. But somebody in the control room is looking at it, and then the controller says, okay, the stamp's closed, reports it, now we need to open it. So the controller is what will tell maybe this robotic arm to lift up. So the controller will often feed into something up here. When I was working at the paper mill, we actually had a pretty cool program we call supervisory control. They're looking at the price of fuel and saying, okay, well, this fuel today is cheaper than this fuel. So we're actually going to use natural gas instead of burning our bark. And so this is usually like a server somewhere. It's making these decisions, feeding it to the controller, sensors, actuators. Does that kind of make sense? Nobody has any questions about how that? Okay. If you guys have any questions about it, just throw it out there. I'm fine with that. Here they are. Here's a real this would be the controllers that's in a box somewhere on the field in the plant, something like that. So this is Alan Bradley. I stole this stuff from the internet, the pictures anyway.
It's like I stole this equipment.
Yeah, I just downloaded it. No, I didn't do that. So this is actually a physical lab that we have at Mississippi State. Because, those guys in SCADA systems, y'all come in. The physical SCADA systems, they usually won't let you attack their system. They won't let you walk in and say, oh yeah, you can do a pen test on all our controllers. Y'all heard Robert talk this morning about uptime? Like that, they reward employees, at least at the paper mill, for uptime. If you were up 365 days out of the year, you're good. So there's no way they're going to let us come in and test those systems, try to penetrate. So what Dr. Morris and Dr. Vaughn, what they did is they bought some equipment, some SCADA equipment, put it in the lab. This is a little gas pipeline. That's a valve right there. There's a compressor underneath that has a pressure sensor. This is supposed to sort these pucks based on color, go to one way and the other. And these are some of the displays that you would see to control them. This is helpful because now we can actually attack a real controller. You can look at how it responds to a real process. One of the things that coming into my research that we've thought of, and I think many people know is a problem, is that's a really small, that pipeline is maybe as big as this table. So the response of that is not very big. We only have one controller under there, so You don't have a diverse control system. It's not really representative of what they're doing in the field. And it's expensive. Like, all this equipment is like $200,000, and it's still just lab scale stuff. So it's hard for researchers who want to look at security of SCADA systems to manufacture that equipment. So why do we want to virtualize it? We have all this stuff. My favorite is the bottom. You can blow stuff up. This is the Death Star blowing up. You guys already saw Star Wars, so, but there. Bam. Yeah, portable, you can take, so what I'm about to show you is a virtual lab that we are building at Mississippi State. It's portable. I could give it to you, any of you if you wanted it. We can send it to you. Yeah. So if you want it, I've got cards, just send me an email so y'all can have it. You can distribute it across the internet. You can expand it if you want to. It's free. You know, you can break it and then reset it. So it's got a bunch of stuff that you can't do in real systems. So, and you can blow it up again. So, just a little bit so y'all understand some of the attacks I'm going to show you. This comes from Wikipedia. I think they call it the de facto standard of SCADA communications, but Modbus. Anybody heard of Modbus before? Y'all heard of Modbus? Okay, so y'all know. So y'all know a little bit about this. I think one of the things that's most important to me is that in Modbus, they have this unit identifier. So you can only have 255 Modbus devices on a, like if you're thinking a flat network, because it has to have a device number between 1 and 255. Well, native Modbus, if you plug up a device, the device says, start sending messages as device number 4. No one checks natively to see if you really are device 4. There's no authentication built into Modbus. Yeah, so you can see where this is going. But no authentication. Nobody knows, so I'm going to show that in just a second. This is some of the commands that you can do in Modbus. So typical transactions usually involve your reading and your writing. So back and forth, you're reading data from one device, you're writing data back and forth. Even the HMI, when I'll show it later, it's just reading from a virtual PLC and then it's writing commands back. So, and all this is on Wikipedia. It's a great article on Modbus if any of y'all are interested in Modbus. Really good. So as a part of our SCADA simulation, virtual SCADA lab, we've simulated the process, the controller. We actually have a real HMI, I'll show you that, and an attacker. So, this is the pipeline model this is the scenario we modeled. It's just like what we have in the lab in our case. So it's modeling, the way it works is we have a compressor, we have a valve, compressor turns on, it's pumping up. If the valve is open or closed, pressure, valve is closed, pressure goes up. Valve is open, it may stabilize. The pump is off, valve is open, pressure goes down. If both are off, it does nothing. The guy who started before me, he just used these equations to model it real simply. My work has actually been, we've taken, are y'all familiar with Simulink, MATLAB Simulink? Any of y'all used it before? Okay, yeah, professionals in the process simulation, like, they use Simulink to model processes, larger processes than this. So part of my work has been to replace this model with Simulink. So now we're actually talking to, Simulink has a graphic model. I had a picture, but I left my flash drive stuck in my computer at the office, so I apologize. But we also have a controller that we're emulating. And I think there's several important aspects of what we're doing in terms of controller modeling, but probably one of the most important is that it's using Modbus. It's actually talking. So if you pull up Wireshark, which I probably will do, and you look at the traffic, all you see is Modbus traffic. Nobody knows that it's not a real controller on the network, which is important for attacks, and it's also important for data creation. Also, it is functioning the way a PLC should. It's emulating the ladder logic that they use in a PLC. So, yep, we have these 2 HMIs and 3 attacks. So, I'm actually going to show you guys that real quick rather than keep on talking about it. So, let me bring this up right here. Yeah. So does anyone, does this look actually familiar to any of y'all? Did you see it on the earlier slide? Did you see the, oh, come on. Maybe I don't want to do that. Oh, I'll just do this thing. You saw it from Dr. Vaughn?
We saw this from Dr. Vaughn.
Ah, okay, cool. Did he show this same,
Yeah.
Okay. So, for those of you who heard me talking earlier, Dr. Vaughn was at Mississippi State. He was integral to the building of that physical lab. But this is actually the HMI that they use in the lab. So, connected to a physical PLC, they're using this display. It's going to, when I turn it on, well, actually right now, it's requesting data from a virtual PLC using Modbus as a protocol. So right now, this doesn't know it's not talking to a regular PLC. But I'm going to turn it on, so you can see these just look like buttons that you might actually have. But when I turn it in automatic, it's going to try to come up to the pressure set point that I have programmed inside. So you can see up here there's a pressure, but it's a lot easier to see if I bring it to this trend. So, and in case I didn't explain it earlier, the way that a lot of times pressure controls work is that the set point is you're telling it, I want this pressure. In this case, I've set it to 5 pounds. Does anybody know anything about PID controls? Okay, I'm not going to explain it. That's how they actually implement a little bit. Okay, yeah, that's how they decide whether to open or close this valve. It's really mathematical and a little complicated, but so here you can see the pressure as this is real time, and this is trending the pressure. So right now, this HMI can't tell you the difference between. It doesn't know that it's not talking to a real PLC. It doesn't know that that's not real. Pressure values coming through. It's just reporting what it sees. So I'll show you guys some of the Modbus traffic, and then I'll show you an attack against the system, and then maybe talk a little bit about why. So you guys all know Wireshark, I'm sure. Does anyone not know what Wireshark is? Okay, everyone knows what Wireshark is? Okay, I would hope so. Huh. I would hope so, but just in case. So what I'm going to do is on the computer that's running the virtual PLC emulation, I'm going to start capturing some of this data. Yeah, here we go. Sweet. Yeah. So y'all saw I broke down some of the Modbus frames earlier. Well, here's data that Wireshark sees coming across the wire. Yeah, I'm going to bring this up a little bit. Yeah. So 10.128.0.6 is where I'm running the virtual PLC. 10.128.0.3 is where the HMI, that's its IP address. And you can see right here when I open this up that, yeah, here we go. So Wireshark thinks that this is a Modbus packet of link 5 that's wanting to talk to unit 4, and .6 is responding as a response to a request to read coils, which is normal Modbus traffic. That's one of these read requests that I was talking about earlier. So if you're looking at data across the wire, you can't tell this isn't regular Modbus, regular SCADA traffic, which I think is pretty cool. I think is important for creating SCADA datasets, which I'll talk about in a second. But what I want to show you next is it relates to some of the vulnerabilities of Modbus that I mentioned earlier. So here's the system. It's running as usual, running about 5 pounds of pressure. Well, because Modbus doesn't authenticate to tell you if you have a new device that's added on the network or something like that, there's no native authentication to say, oh, well, that's not actually device number 12. What I'm going to do is I'm going to inject a set point into the virtual system, and the virtual system is just going to respond. It's going to respond as if it had received a new set point request. So, give me just a second, and I'll show you. All right, cool. Oh. That's not cool. Okay. So what I'm going to do is I'm actually going to modify the set point of the system that's running. And really all I'm doing is I'm creating a Modbus packet, and I'm sending it to the virtual PLC. It's also a denial of service attack at the same time, but see if we can see it. Actually, I should show you that a little bit better. Let me change something here. I'll wait for this to close out. So what this attack does, while I wait for it to restart. So since I have my virtual device that's running at .6, yeah, let me reset this set point for you guys. I have a virtual device that's running, and the HMI it's actually sending this set point value over to a virtual PLC. The virtual PLC sends back pressure values. I'll explain that in a second. But it sends it at a certain rate. So it's sending it it's maybe once a second. It's sending a write request. It gets back the data that it was reading. So what I'm going to do when this returns down to normal is when I attack from a completely different device, I'm going to just basically spam the virtual device, the virtual PLC, so that everything that HMI was trying to write, the virtual PLC doesn't hear it anymore. And then when I'm spamming with real Modbus traffic, telling it rewrite the set point. So when I tell it to modify the set point, yeah. So these are the packets that are coming across. Yeah, here we go. So this was the PLC operating at normal, but right here you can see that it started to get a new set point value. You can see it changing over here. But as you guys saw, I haven't changed that value at all from here. I didn't change it to 130. I didn't change it to 131, 132. So basically what you're seeing is a successful set point modification attack against a virtual PLC. So, and it's going to run for a little while. So if you have any questions about, do you understand how I did that? Kind of? Is it confusing? No? If you do, you can ask. Okay.
Where was that attack come from?
That's a good question. In this case, this would probably be like if someone had compromised a machine in the network or something like that. That would probably be the most likely vector for the way that this attack works, because it's actually coming from a computer that would be on the same network. But if you were able to communicate with your PLC, it really wouldn't matter where it comes from the perspective of Modbus. You see how that works?
So,
kind of.
Are there like wireless PLCs where somehow you can wirelessly send communication to
Mhm.
PLCs and you can send Modbus packets to it? You don't necessarily own a machine in the network, but say you run an laptop and try to do something like that.
So you saw some of the pictures I showed of the facilities. What the industry is moving toward, because one of the highest costs in setting up that facility is like running cables. They'll have to run cable probably for almost a mile. So wireless technology is something that's growing in the industry. So yes, sometimes the devices communicate wirelessly. Sometimes the computers that are connected, they're on the same network as the PLCs, and they communicate wirelessly. So if you had a wired connection into the network, you could start. If you had a compromised machine, you could attack. If you had somehow to get onto the network, you could attack. So those are, I think, 3 avenues that I know of for this particular attack. Anybody else have any questions? Okay, so this kind of ties back, I think, into what Ben was saying, but one of the reasons that we're doing this, when we talk about normal traffic, you can see how when we're looking at the traffic that's coming over the network, you're looking at real SCADA traffic. Well, it looks like real SCADA traffic. when we're creating these attacks, this is abnormal SCADA traffic. So this is kind of a tool that we're building to give to SCADA security researchers, and some of our guys in-house are using it so that they can look at, without having to go ask a power plant for data, without having to ask a paper mill for data, they can create real data sets of real SCADA traffic. And they say, okay, yeah, we can use this now to determine the characteristics of malicious data. One of our future research goals is to expand this so it's much larger and much more accurate, so that you can also look at how would this system respond physically, what would happen if you back up the pressure at this point, how did the controllers respond, so you could look at sort of a distributed attack and how it responds. But I think that's mostly what I had when we go through here. But yeah, I just wanted to show you guys what we were doing at Mississippi State, what may be happening in Huntsville soon. Yeah, this is what we're doing in Simulink. It's actually modeling a small. Yeah, that's pretty cool. Yes, sir.
Is there any effort to scale the modeling so that you could have a unit happen together? So you could get simulate a valve ripple, so you can get a pulse that passes through. Is there any effort to do that with the model?
That's what we want to do. That's kind of my next task, is what we're working on. Because right now, see this model you're looking at, which I actually have built. I was going to show you, but I couldn't get it running on my laptop. It just has one pump up there, and then it has a pipe, and it runs through this valve. The next piece where I have it is it's distributed. So just having two pumps and two valves, but that's the sort of thing we want to look at.
Yeah, well, that would be just one unit you just plug in from a software standpoint together, and you could create what you want.
That's what we want to do, yes. So, because we want to be able to have sort of if you could simulate a distributed, maybe like a pipeline, where you're looking at across interstates, you've got hundreds of controllers, different HMI. So yeah, that's our effort. It's aimed at the future. I mean, we're not going to have it this year, but that is what we want to do. So, anybody else have any questions about it? Yeah.
I don't know a lot about SCADA to begin with, but you said in 4 sends a request, it doesn't authenticate and check if 4 is actually 4.
Right.
Why does it work like that? There's what seems to be a few bad sides. What upsides is there to not having authentication?
I think that the reason for the lack of authentication is not really as much pros and cons as it is a relic of the way things. That protocol was designed in '79, and it's really interesting because looking at the history of how these systems evolved, it used to be that the controls were all proprietary systems using protocols that were only used by, like let's say Honeywell. They've got their Honeywell protocol. It doesn't talk to anything outside the plant. It's all local, and it's all Honeywell-specific protocol. So authentication wasn't really a big deal. If you plugged in a device, it pretty much had to be Honeywell or, Allen Bradley or whoever. So that's kind of the way it worked in the past. The push has been to have these devices so that they can talk upwards. So maybe a manager who's in New York can look at the data. Well, in order to do that, you have to have them all on the same network. If somebody's got to be able to talk regular TCP/IP or something like that. So I think that's why they didn't have authentication, is because they weren't designed with that in mind. There are newer protocols, I think, coming out that have that incorporated as a part of it. Because it's so expensive to replace that stuff, and because uptime is such a huge deal, it's hard to say, oh, well, let's put in a brand new controller. So that's a good question, Dave. Yeah, okay. Anybody else have any questions?
So y'all doing research about the TCP interfacing? Y'all see this wall? How to protect it better?
So I think some of my colleagues are working on that. My work has been actually on building this part, but I know one of the things that they've been doing is, so we create like a huge, well, I say huge, it's a big collection of this network traffic. So what we look at is how do we tell the difference between what's good and what's bad. So that's one of the things that they've been doing. anomaly detection using machine learning algorithms to sort of classify network behavior. So, but we've been building this so that we can build for the network traffic, and by building the network traffic, then we can look at good versus bad. Does that kind of answer your question? Okay. Anybody else? If anybody wants like these, I also have written some lab exercises for students, and there's several universities that are using this stuff. So if anybody wants this, you're welcome to email me and I can put it up where you can actually have this laboratory. It has instructions on how to use it. So yeah, just shoot me an email, and I have some cards if anybody wants one to email me. Y'all can have it. So. Yeah, that's it there too. So, but yeah.